Okay?
Our next speaker is Itai Peer, the same advisor from University, and he will talk how we use how to compensate the reverberation effect that we just heard.
Hello, thank you. My name is Itai Peer, as we say. I'm an advisor and Niv Ziegler. We talk about speaker compensation for reverberation for speaker verification. And you see, reverberant is already talking in previous seminars. It's a warm reflection. The warm reflection from the walls is convoluted. It's like a convoluted noise. It's the great speech intelligibility and the performance of the speaker verification system. We talk about text-independent speaker verification. You verify the speaker by free speech, not by password or something like that. Okay, I will talk briefly about speaker verification systems, the more or less baseline systems. We talk about the main approach here. It's called compensation of misses factors, CNF. It's the main approach to compensate the reverberation. I talk about reverberation, of course. I integrated the CNF with the reverberant model matching. It's a previous approach of ours to deal with the reverberation, and also reverberation classification, and of course experimental result. Start, of course, by speaker verification system. The system has two main stages. The training stage, which the system learn the speaker features and create statistical model. First, of course, there is the feature extraction. We divide the speech into small segments, extract acoustic features vectors, the MFCC in our cases. So we have many feature vectors for each speech segment. Then create a target model or speaker model for this speaker. We are estimating the parameter of GMM, Gaussian mixture model, for each speaker. We also have a background model. I will talk a bit more about it later. It's a model. It's created by estimate GMM of many speakers, a large number of speakers. It's supposed to represent the world, the rest of the world, something like that. Anyway, the second stage, of course, is the testing part. We extract features from the test segment. The one claimed to be the speaker, we call it a test segment. We extract the MFCC feature from the speech. Then we compare likelihood, log likelihood ratio of this feature with the target model and with the background model. The targets represent the claim that the test is the speaker. The background model represents the claim that it is not, it is an imposter. So we have a log likelihood ratio. We calculate score, and then if the score is higher than the threshold, we accept him as the speaker, otherwise we reject. Now, the main problems in speaker verification, at least in the literature, is a mismatch condition, mismatch acoustic condition. The different environment in the training and different acoustic environment in the training and the testing. That means that the system learns the speaker features using NSET, but NSET or some kind of communication device, and when she has to test, the guy called in cell phone, so it's have a different effect, different filters. What can also affect is the other communication channel, communication device, background noise, and room acoustic reverberation, which is the main topic in this seminar. Well, compensation method for mismatch condition usually divided into 3 domains. The first is the feature domain. It's supposed to go red now. Feature domain, you attempt to normalize the feature vectors to compensate the channel effect. CMS, feature mapping, joint factor analysis are common approaches. Second approach is model domain. You attempt to modify the speaker model, the target model, to adapt it to the test, to the acoustic of the test segment. SMS, eigen channel modeling, etc. Third approach, and most simple, is the score normalization. You normalize the score, the log-likelihood ratio, according to the model or according to the test. I'm not going to much into detail. Now, let's talk about the eigen channel modeling, which is the basic of the method. First, I will talk about the adaptive GMM, what it is actually is. We're using the instead of estimating the speaker Gaussian mixture model by maximum likelihood approach, we use the map adaptation. We use the background model as a priori probability for the speech, for the voice feature, and using the feature extracted from the training data, we adapt the mixture, mixture mean vectors, only the averages, while the covariance metrics remain untouched, remain constant. That means that every speaker can represent only by the mean of the mixture vectors. So if we join all the mean together, we get the super vector, what's called the super vector. It's actually a one vector with a very large size. And this is the super vector, usually about 20 to 50,000, the dimension of the super vector. And the eigen channel modeling is the variability, modeling the variability of this super vector. Now let's suppose this is the super vector space. Let's assume we have several conversations from each speaker. We train one model for each conversation and extract the super vector for this conversation. So every dot here is a super vector of conversation from the speakers. Then we want to see how what is the variability of the speaker super vector. We use it by we estimate covariance metrics. Of course, we cannot have covariance metrics of 2,000 with a rank of 2,000, so 20,000. So we will reduce the rank by using the eigenvector of the largest eigenvalues. That's why this method called the eigenchannel. This variability is usually according to channel effect. Anyway, the CNF, compensation of nuisance factor, use the eigenchannel model. I will not go into detail about the formula, but it used the eigenchannel model to compensate the channel effect in the feature level. Now, room acoustic reverberation is already discussed. Caused by a reverberant room, large distance, many reflection from the room, walls and floor safe. It's a convoluted noise which affect both the spectrum of the speech and cause a smearing effect due to its its long duration of the room impulse response. Okay, our previous approach was a reverberant model matching. What we did is train a target model by synthetically reverberant speech. We convolve the relative clean speech of the training data with the simulated room responses. Then we train additional target models and background models, reverberant target and background models. Then, at the testing stage, we apply reverberation classification, and in case where we decide that the test segment is reverberant, we just use the reverberant target model instead of the clean one. This is, by the way, the same scheme, just shifted some of the boxes. Now, how we integrated it with the CNF, the compensation of nuisance factors. First, we estimate the covariance metrics of the eigen channel according to a reverberant developing group. I will not go too much into detail there. Then, after reverberation classification, if we decide that the test is reverberant, first we apply reverberation compensation according to the CNF. Then we tested it with the reverberant model. So we have two means of reverberation compensation. So let's quickly go about the system and the experiment setup. We use a 26 MFCC feature, 13 MFCC and 13 delta MFCC. We use CMS, subtraction in all the experiment with and without reverberation. We use adaptive GMM training. We use for the testing data we use measure room response, while for the training data we use simulated. We try to make it a bit more realistic scenario. The database taken from the NIST 99 speaker evaluation corpora. Also, scarmerization ZT norm used in each experiment, both clean and reverberant. I will talk a bit about reverberation classification. The question is how to decide if the test segment is clean or reverberant. Clean is not exactly clean, but unreverberant, you can say. Anyway, we use the clean background model, which were trained on large number of speakers with clean speech. We also have the reverberant background model, trained on large number of speakers with reverberant speech. After we extract the feature of the test segment, we just calculate the likelihood with each background model, and according to maximum likelihood, we decide if the test is reverberant or not. As you see from the table, the results are quite accurate. About 99% of the clean and the reverberant test were classified accordingly. So 98% of the clean classified as clean, 99 is the reverberant, classified as reverberant. Now let's talk about the result. First, we have two means of measuring the speaker verification result: equal error rate and minimum DCF detection cost function, which give more emphasis for the low false alarm in order to detect more imposters. First, the degradation from the baseline system without reverberation compensation. As you can see, the equal error rate and the mean DCF are double and even triple in case of reverberation. The higher reverberation time, the higher the degradation. So we use the CNF, the compensation nuisance factor, with and without the integration of the reverberant model matching. For low reverberation time, we see that the CNF alone works much better. It's actually as it is a channel compensation method designed for a channel effect with usually low reverberation time, lower smell effect. So it's work better for the low reverberation time. Compensate the degradation almost completely. However, for higher reverberation time, the CNF work much worse. The integration with the reverberant model matching compensates better. You see the equal rate reduced from 16 to a bit less than 10%. The DCF reduced from 6 to 379. Concluding all the reverberation, and at least all the reverberation used in the testing, we see that the results are quite similar of the CNF with and without the reverberant model matching. There is slight advantage for the use of reverberant model matching. Anyway, we compensate the effect quite significantly. We compensate the effect of reverberation. For conclusion, we see that reverberation degrades very significantly the performance of speaker verification. The CNF, compensation of nuisance factor, improved performance, especially for low reverberation time. Integration with the reverberant model matching helped for higher reverberation time, and the reverberation classification with the background model is quite accurate, so this is also a very important conclusion. Well, thank you for listening. Any questions?
Yes, time for one or two quick questions.
Do you always use the classifier between reverberation and clean data, even in the clean test?
Even if the clean test, about only 1% of the clean test was classified as reverberant.
The second thing, Mark, always suspicious when you have zero error totally, even in clean data.
Well, actually we use reverberation classification for improved previous work. We have several reverberant model, so we have to decide for low reverberation, medium and high reverberation, then we have much higher
I'm
error rate.
talking about the last table, the results of verification with
This
zero,
one?
yes.
It's better to add one mistake.
Yes, totally.
Zero? Actually,
What it means, this dash.
well, actually, it's because the clean tested almost every time we classify as clean, the results are very similar. I don't remember the exact number, but they were very similar to this. I don't know why I moved it. It's very similar because 99% of the clean were classified as clean, and the 1% that were not much degraded by using the reverberant model or the CNF. It's not degraded clean speech very significantly.
Another question? Thank you again.